Hello everyone, welcome back to, I think it's recording. Welcome back to Advanced Track Workshop 4. Today we're going to be talking about embeddings, RNNs, LSTMs, and transformers. This is probably one of our longest workshops because we didn't have this part last time. And then we added this part this time, and it's probably the most complex thing we're going to talk about in this entire workshop. But it is very important because transformers are actually the backbone of something called ChatGPT. You may have heard of. And basically, all of these are very, very integral to a lot of natural language processing, aka like dealing with text instead of images, which we have been talking about for the past 3 workshops. And we have a guest lecturer today for part of it. This is Pratik. He is from Project Track, and you will get a taste of what it may be like in Project Tracks when you will be able to learn about these in more detail and perhaps implement it yourself next quarter. So yeah. Again, the asset cluster should contain the slides, and Discord is here, feedback form is here, and yeah. Any questions before we begin? Awesome, let's get started. So again, that's what we're going to be talking about today: word embeddings, RNNs, long short-term memory, and finally transformers. So first, let's begin with word embeddings.
Right. So basically, when you use text in neural networks, you can have a fundamental problem, right? That your text is a word and your neural network expects some sort of numeric vector as the input. So what you really need is some sort of a function that can take your word in and output a numeric vector. So like your initial approach might be to be like, well, we can just use the ASCII values of the text, right? Because that converts all of our words into numbers. Or we can just use like arbitrary mapping. So like A equals 1, B equals 2, and so on. But the thing is, that's really not gonna work, because what you're gonna end up doing is you're gonna introduce relationships between your words that don't make sense. So like, when you use pictures, then you have pixel values, then it makes sense because a higher number means brighter pixel. But if you just use a meaningless embedding, then you could get stuff like lowercase a plus like exclamation mark equals capital B, right? It's not going to make sense. So what we need is some sort of function that like maps all of our words to vectors that can be used for computing other words and like other values. So a naive approach would just be, we take all of our documents, right? So let's say we're doing like classifying movie reviews as positive or negative. Now, what we can do is just take a number of words that are important, and for each of those words, we can count their occurrences. So again, this is an example of a movie review, and the approach is called bag of words, right? We take all of the words that we think could be important. Basically, we're making a list of all the words in our entire vocabulary, and we count their occurrences. And then we take those numbers and use that vector as the input for our neural network. Now, this isn't the best idea because look at these 2 sentences. If you were to just count the number of words, in these sentences, then they would both be exactly the same, even though their meaning is completely different. Again, the bag of words approach can't really tell the difference between different sentences as long as they're made of the same words. This also can't use punctuation, because when we just count number of words, we're excluding a lot of information that's in our sentence because it just doesn't get captured by our vocabulary. And yeah, you've probably heard this. You've probably heard this example a lot in your English classes as an example of why punctuation is important. And it's just as important when you're using natural language processing to not just like skip using punctuation because it gives you an easier model. So the solution is we use embeddings. So this is basically really straightforward. We take all of our words, right? And you will use one-hot encoding. So let's say we have 1,000 words in our vocabulary. We make a matrix that has 1,000 positions in them, and all of them are 0 except for the one word that we're using. And we use that to index this giant random matrix of random numbers. So we get a bunch of random numbers that represent this word. Now, while this might be used at first, if we just use this, then through machine learning and backpropagation, by when we're done training our model, it's going to change these numbers into some sort of number that like effectively represent the meaning that that word has.
Yeah, and just to reiterate, because we haven't really talked about one-hot encodings yet. So what one-hot encoding really means is we begin by basically saying, okay, for every single word in our dictionary of all possible words that we can have in our input texts, for every single unique word, we assign basically a number to it. So for example, I will be 1, you will be 2, and like, I don't know, pizza will be 3, and so on and so forth, right? And then we try to represent those words as a vector. So for example, in this case of like a dictionary with just 5 words, a word with the index 1 will have 1, 0, 0, 0, 0. A word that is given the number 2 will be 0, 1, 0, 0, 0. Or with number 3, 0, 0, 1, 0, 0, and you get the point. So that's something called one-hot encoding. And basically what we want to do, and basically what we can do is by using this one-hot encoding vectors, when we multiply it with this matrix. So in this case, because the 4th number is 1, right? And we do the multiplication, all it does is just says select the 4th row. It's just like a mathematical trick that allows us to do that, right? And this embedding weight matrix is the real thing that we are learning. Because basically what we're trying to do is we first, just like with most neural networks, we initialize this to just any sort of random values, right? And what we are trying to do is to say, how can we have a bunch of vectors, each of these vectors corresponding to our inputs vectors, or each vector will correspond to our every single unique word in the dictionary. How can we make sure that these vectors are trained in such a way that they're meaningful? So, for example, if let's say 2 words that are very similar to each other will be very similar to each other in vector form, and 2 words that are perhaps very different from each other will be very different from each other in vector form. That's kind of our goal here of what we're doing with word embeddings is, can we find some numerical way to represent text, specifically natural language, in such a way that it somehow preserves the meaning of those words? And that's what word embeddings are. Next slide.
So here you can see a bunch of examples of like how these words could relate. Essentially, you want to have your words convert to vectors such that they have meaningful relationships between them. So this is the kind of an example where if you one like way to check if your words are meaningful is that you take the word king, you take it convert to a vector, subtract the vector for man and add the vector for woman. You should get something close to the vector for queen. See what I mean? So yeah, this can be done by basically using pre-trained embeddings as well. So one way, so like in these, just showed you an example where you use a bunch of random numbers and you basically just use backpropagation and hope that the vector, it turns those numbers into make sense. Another way of doing that is just by using pre-trained embeddings. So basically, people have already made neural networks where they use like these words for a lot of complicated tasks, right? So like predicting the next word in the sequence or filling in missing words. And what these neural networks do is that they convert these words to vectors that make a lot of sense. And we can give our model the head start by basically just using those values that they derived. Well, one example is word to vec, although it was derived a little differently. And we basically just use it as a starting point. And then we fine tune these vectors to suit our specific task.
Yeah. And just to kind of further clarify how people have really, gone on to train these things. So basically how they're going to do this is, first, you kind of, initialize these random weight embedding matrix to some just random values. Then what you say is you then try to train, again, randomly initialized neural network. And in this case, it will just be like a fully connected neural network. If you remember from previous lectures, it's just previous workshops, it's just kind of vector. We do a bunch of matrix multiplications plus additions, some activations. And basically all it's trying to do is, let's say, given, like a sentence, it will mask off one of those words. And it basically says, all right, try to guess what that word is. Right. And as it is trained on that task, we use things like gradient descent or the other optimization techniques we have discussed before. What ends up happening is, because not only are we nudging the weights of the actual neural network that's trying to do the prediction around, we're also going to be nudging this embedding weight matrix around. And by doing so, what we're able to do is basically the weight embeddings are able to learn a representation that actually numerically that kind of represents word meaning, because think of it this way, if it didn't numerically represent the word meanings, then it wouldn't be able to do the task of, given some words around it, what is this word in a natural language sentence? So only if it contained these sort of natural semantic meanings, 2 words that mean the same are close together numerically, and 2 words that are different are, different from each other numerically, will then the neural network being attached to it be able to do the prediction task. Does that make sense? Yes.
How do you get a input vector?
Like this one?
Yeah.
Oh, the one-hot vector is just, if you remember, like if we have a bunch of words, we just randomly assign numbers to every single one, like unique numbers to every single one of the words. For example, like imagine just putting them into a list and there's just indexes of the list, and you just take the one-hots. It's basically a really convenient way for us to do, use a mathematical way to represent, select this entry in the matrix. That's all it is. So like this corresponds to word 1, word 2, word 3, word 4, word 5. And you can imagine how it can get much bigger with much bigger words. And if you have a lot more words, this actual embedding weight matrix may be lighter in that we're using more numbers, more dimensions to represent each word. Yes.
So the vector would also be larger then? Like this is just kind of like a smaller example.
Yeah, this is a smaller example. Like usually like for embedding weights, because if you think about it, this vector is just 4-dimensional, but usually it will be like, let's say 128 dimensional, for example, or even larger. And if you and the total height of this matrix will be the number of words you have in your dictionary.
And is it like selecting a whole row, or can it be like a portion of a row, like depending on?
It usually selects the whole row because it's just like mathematically easier, you know. Does that make sense, over? Yes.
But, it doesn't make sense. How does that make a king closer to a man, but not a woman?
Well, you see, basically, right? Let's say they're all random to begin with, but then you train this model on some sort of task that requires it to learn the meaning of these words, right? So let's say you're trying to predict the next word in the sentence, or you're trying to like fill in the missing words in a paragraph after you've like masked them out. Then as it trains, it has to learn what these words mean. You see what I mean? Because if it doesn't learn to some extent what these words mean, it can't really fulfill these tasks.
Yeah.
So embedded weights are gonna change.
Yeah, exactly. So they start off as like completely useless, but as you train on more and more tasks, you can basically get them to have like some sort of a useful meaning. And then you can take those numbers out and use them for other natural language processing tasks using that meaning that's already derived.
Yeah. And one more thing is like this side effect is only like something interesting that people have noticed. I don't think there is a sort of like rigorous theoretical explanation of why this works, why we can do king minus man plus woman roughly equally to queen. It's just something that people have noticed after they have trained these models. They're like, hey, that's pretty cool. So that's just something I've noticed. It's not really something that we set out to do. It's just something. It's almost like a byproduct. And just kind of like almost like a note, like a terminology thing. In the future, when we're referring to words or inputs, we're almost assuming that we have passed those natural language words through this, embedding process. And we're saying words, we're really referring to vector representations of these words. And when we are referring to things, like for example, generating words, then the generating words is really just, they generate a certain vector. We go look at our entire list of embeddings, look for the vector of the word that's the closest to the vector that's generated and saying, okay, that's our output word. Does that make sense? Okay. All right. So now we're going to jump to something a little bit different, but it will make sense when we talk about transformers why these two things are related. But let's talk about RNNs, or recurrent neural networks.
As Jordan said, RNNs are also known as recurrent neural networks. And basically, if we kind of like look at like what we've covered so far in this workshop track, like we've looked at CNNs, right? And when we compare the model of CNNs to RNNs, we actually notice that we have quite a few similarities. So the first thing is that they both use a feed-forward network in order to train their input, and then the input is non-sequential and the data is static, and the input space is independent from other elements. And so that's kind of like what we've been going over so far. However, with RNNs, things are like slightly different because RNNs are used more for sequential data. So in this case, when we have like CNNs, right, the first input might be of like, let's say like a plant, and the second input might be of like maybe like a flower. So the data doesn't exactly need to be in order. We can train the flower before you train the plant, right? It's not going to change the output. However, when we're dealing with things such as like a video, or let's say like a clip of like somebody talking, right? The order that we process the data is actually going to have a big impact on our output. And we need to have a model that is able to properly process this type of data, which is where we have RNNs come in. Yeah, and so the main thing why it is very important that we process this data sequentially is because the input from like one part of the video could affect the other part of the video. So essentially the input from one section and the output that you get from it might affect the input of like the next training round, which is important, which is why we need to keep everything in order. So like, for example, like if we have like a bouncing ball, right? In order to predict where the ball will bounce next, we need to understand everything that's happened before then. Does this kind of make sense? Right, yeah, and so just some examples of like sequence data, we have like audio, text, as well as like video, right? And then I guess, does anybody have any like other ideas of what like sequential data might be?
Would gameplay AI more suitable for RNN?
Sort of. Some gameplay AI can be based on RNNs, but most of them are actually based on something that's almost kind of an extension of RNNs called reinforcement learning. The difference is RNNs, we have our data predefined, right? We have a sequence of videos that we're just going to be feeding in not all at once, but it's predefined in our data set. Whereas with gameplay, usually it will, it will be initialized randomly. It will do something. And then by the feedback of the game, it's going to then use that feedback to then train itself. And it's going to do some more things. It's going to use that feedback to train itself. That is reinforcement learning, where the model itself is almost creating data by interacting with whatever environment it is being put in. So it is a little bit different, but like the idea of like time series data being fed into the model sequentially is roughly the same. Yeah. Does that make sense? And just another things, I don't think reinforcement learning models necessarily have to be RNNs. They can also just be static feed-forward networks, but there are also some that are kind of based on RNNs as well, depending on how you design your model. Yeah.
Good response. All right. Yeah, so just general like concepts regarding RNNs. We're not going to go into too much detail because they're not used that much anymore, but they serve as a very important foundation for transformers, which we're going to be going over later in this workshop. Yeah, so like I said before, RNNs are typically used in, or at least like the overall like theory behind it is used in speech recognition, video translation, as well as video classification, right? And as you notice with all of these types of data, they're all sequential, like everything must be in order or else things are just not going to make sense. So here order matters versus in a CNN, not so much, right? We can process the data whatever we want and we'll still get pretty much the same output. Yeah, and so when we look at the structure of an RNN, we can actually see that is very similar to what we've been kind of going over for the past couple of weeks, right? So before in like a typical CNN, we'll have like our input, our hidden layer where we train everything, learn our like weights and biases, right? And then we have our output, which is our kind of like what we want it to like answer or like the prediction, right? However, in RNNs, things are like a little bit different, right? Because remember that the output or an input might affect the training process for the next input, right? So like the first second of the video might also affect the second of the video. So if we have like our input here, right? Instead of just having a hidden layer, we're actually going to take the previous hidden layer that we just trained, and we're going to put all of that into our hidden layer, which will train both the input and the old layer. So we can have that kind of sequential data, and then we'll get the output. So does this distinction kind of make sense, like why we're doing this? Okay, solid. All right, yeah, and so this is kind of like a more mathematical visualization of the slide before. So as you can see, we have our previous layer, all of like the weights and biases from our previous hidden layer, as well as our input, which is like a new input, a new layer, and we're going to train both of them together, and then we'll get our output, which is over there. Yeah, and then another very important thing to also realize about RNNs is that they share the same parameters across pretty much all of their steps. And so essentially, this is very beneficial because it greatly reduces the total numbers of parameters we need to learn. So it's very important for efficiency, right? And so the great thing about this is that because we do rely on our like previous hidden layers, it means that we don't need to constantly like retrain weights and stuff. We're able to share the weights between layers that allows us to kind of learn better when we input like a new input into like the hidden layer and then test for the output.
And just kind of one quick thing, like when we say like, oh, they're sharing weights, it's really just one model that we're using. So basically, let's say we have a sequence of images or text or whatever. We start from the first thing that we're looking at. We take that first thing, we feed it into our model, and the model will generate some sort of output, right? We kind of keep track of the output. We say, okay, let's store the output here, but we also make a copy of the outputs, and we say, okay, we make a copy of the outputs, take the second thing in the sequence, put both of those in at the same time. And we say both of those in at the same time, but the first time, that's like a different input size, right? So usually what we do is like for the very first item, for the previous input, we just put like a bunch of zeros, because zeros usually in neural networks just means do nothing, because 0 multiplied by anything is just still 0. So then the second output, with the second input with the output for the first input, you'll get an output. You take the output again, take the third thing, put it in. Take the output again, take the fourth thing, put it in. So it's this kind of repetitive process. We're applying, again, the same weights. A lot of times you will see this sort of unfolded view of the RNN, and it can be kind of confusing. It's like, wait, so are there like 5 different networks? No, it's just one network. And then at the very end, because we have a bunch of outputs. So let's say we have a bunch of these outputs, and what we can do is we can, like take these outputs, we can feed it into further things, or let's say if all the RNN is trying to do is generate a sequence of text, we can just say, okay, do all these match correctly, right? So at the very end, our loss function, aka how do we evaluate this model is doing well, is just something we can do with these outputs. And when we have these outputs, then we can calculate the gradient and do everything, and basically the model weights itself will be nudged around, not just based on the criteria of like, oh, we have the first input, the output of the first inputs match what its label is supposed to be, but something more than that, where it is something like does the output of the first input and the output of the second input plus the output of the first input plus all of these. So suddenly you have this kind of gradient, this kind of nudging around information that is coming from a much wider set of data. And because we're feeding them in sequentially, you also have the fact that this model kind of has the information that this is supposed to come before, input 1 is supposed to come before input 2. So that's kind of roughly how RNNs work, and why you can see how like it's like different from what we have been talking about for the past like few workshops. Yes.
So that circle node actually represents like an entire model.
Yeah, it basically represents an entire model. Like like for images, it may be like for images, it may be a convolutional neural network, right? But for like text data, where it's just like a vector, you may have just a normal, fully connected neural network, et cetera, et cetera. Like you can have any sort of architecture here. We're kind of abstracting it out as just like this one big node that is able to take an input and spit out an output. So does that make sense?
So the weight of the model will only be updated when the entire sequence is inputted into the.
Yes, that is usually the case. There are ways for you to do like almost like dynamic upgrading, like updating, where you can just like train like a sequence of it and do updating. But then again, like that is usually up to implementation details. But typically you would pass in your entire sequence, and then you will do like your whole loss function, backpropagation, or basically calculating the gradients and doing gradient descent thing. Because otherwise they would not have seen the whole sequence. Right. Okay. Any questions? Cool. Let's continue.
Yeah, just like
It's just that, but
yeah,
more.
pretty much what Jordan said. Yeah, just the main thing to get out of this part is that the parameters are shared throughout like the entire model. And so that's pretty much like what allows RNNs to be able to process sequential data in this manner.
Yeah.
And so just to kind of discuss like some of the cons of RNNs. Yeah, so like while they are great with like taking account like historical information for like sequential data, as well as like processing like info of any length, and having the weights that are shared across time allows us to kind of like efficiently understand like this type of data. They do have a couple drawbacks, mainly that computation can be quite slow, and because of like the RNN's capacity, like sometimes it has difficulty accessing information from a long time ago. So while it is able to remember like previous information, it's not really able to remember that much, right? And then it's not also able to consider any future input for the current state. It's only able to kind of like go backwards in time. And then a really big one is that the vanishing gradient problem becomes apparent over large times.
Yeah, go ahead. Yeah.
Solid.
So the solution to all those problems is something called short-term memory. And I'm going to preface this right here. Pretty much no one does this anymore, short-term memory. The reason why we're covering it, in fact, we're probably going to be cutting this down way more next time, but then I'm also going to be going through this quite fast. But the reason why we're covering this is kind of like by learning class models, it's able to see how good transformers are, because transformers can seem kind of arbitrary in that, wait, so what exact problem does this solve? It's because this is what people were dealing with for natural language processing and video processing before transformers came along. So basically, the problem with RNNs is as a process more steps, is trouble retaining information from previous steps. And And the reason is this: if you remember, vanishing gradient, and again, these were generally developed before ReLU was a thing. So because we have sigmoid and tan H, where the derivatives are less than 1 for in most cases, what happens is, think about this: when we take the first input, when we have, let's say, input 100. Let's say we have a sequence of 100 things. Do you think, like input 100 and the output from input 99? Do you think the output from input 99 will contain information about input 1? It probably would a little bit, but the amount of information in input 1 probably will not be very much, because as you're passing, the outputs of the model into itself plus new inputs, you're adding, they almost have to store more and more and more and more information. And what happens is you actually have trouble retaining information from previous steps, because it's kind of like almost exponential. If that's, as you're feeding in more and more and more data, it is unable to choose which pieces of information is more important than others. For example, if you think about the sentence, I went to the supermarket today. I is very important because it indicates, the subject in the sentence. Went, kind of important, to the not important at all. Supermarket is very important. So only I and supermarket is really the most important thing in the sentence. However, when we're parsing these words, when we get to the part about supermarkets, because we have all these kind of filler words in the middle, we may not have, the model may not be remembering much of the information of I, right? And that can be problematic because it is not able to, again, pick and choose. This piece of information important, I'm going to remember it for a long time, versus this piece of information is not very important, I'm going to chuck it away, or I'm going to just only put a tiny bit of it in my model output. And that is what, and that is a phenomenon known as short-term memory, aka it doesn't remember stuff. And to solve that, we're going to do break time right after this. We have something called long short-term memory. And basically, long short-term memory solves two issues. First, the vanishing gradient issue, which is the whole part about how you're not able to retain information over time. But most importantly, the long-term memory loss issue. And the cons is it cannot be parallelized. In fact, the problem with both RNNs and LSTMs is that it's very difficult to parallelize them, because you're relying on the output of the previous inputs to then do the next iteration. So this, because it is iterative, you cannot parallelize this. And if you think about a dependency graph, for example, the current inputs, right, the next input depends on the previous one. So it becomes very difficult to parallelize. And that's also something, oddly enough, that transformers manage to solve. So this is something called the LSTM module. And before I move on, do you guys have any questions regarding why LSTMs exist and your problem with RNNs and stuff like that? Okay, cool. So the LSTM module attempts to solve this via this general sort of architecture here. And again, with a lot of these, all of these are basically weights, right? They're weights that it can't just be one layer neural network, or it can be something way more complicated. It can be, if you're talking about images, it can be a bunch of CNNs stacked on top of each other. We're just kind of abstracting all of these out because we're kind of looking at how all these trainable weights are interacting with each other, right? So the LSTM has 4 gates, and this is what allows it to have the ability to pick and choose between short-term memory and long-term memory. And the first one is the forget gate, which computes what information you want to forget from the LSTM memory. The second one is the store gate, which is compute what information you want to add to the LSTM memory. The update, which is basically taking these 2 bits of information and putting them together. And finally, the outputs, which is to deduce the output from the current time step. And we're going to go through them one by one, so it is very clear what is going on. So there's something called the LSTM cell, which is basically kind of this one long thing that goes through it. And you can think of this cell state as a sort of conveyor belt that stores all the important memory from all the previous time steps. Because over each time step, the cell state can be updated with gates that process the input and previous hidden layer outputs, right? So if you think about here, because we're going to be feeding in sequential data, we have kind of data t-1 to data t. This kind of, it's like a conveyor belt. You can kind of imagine all of these being kind of just duplicated along, and then with t-2, t-3, it's kind of that way. And because you have this massive gate of information being remembered, it is able to have knowledge about long-term information. And these are the gates that basically helps us to store extra information or forget extra information, et cetera, et cetera. Does that make sense? Yeah. So that's kind of like a general overview of what it's like. So the first gate I want to talk about is the forget gate. Basically, what this gate does is, so this is our input, right? So imagine we have a bunch of x's, xt minus 1, x of t, xt plus 1, and that's kind of like our sequential data. So when we feed in a sequential data at any point, we'll be getting what is called the hidden outputs of the previous layer. So some sort of output from the previous layer, and usually we either add them together or we concatenate them together, depends on the model architecture. But basically we bring them together and we feed them into this. And this is basically the forget gate. And all it does is it takes information of the previous states and the current states, and it computes this matrix that basically has generally two values. This matrix can have values of either 1 or 0, or technically anything in between, because again, we're using a sigmoid to kind of limit all of that. And basically all it is when we take, it basically says whenever we have an entry that says 1, we keep this bit of information completely, 100%. But when we have something that is 0, we forget this bit of information completely. And the way we will actually manage to do this is by a multiplication, right? So you can almost think of this as a mask that basically says, if it's 1, remember this bit of information. If it's 0, forget this bit of information. So because remember, when you multiply anything with 0, it's 0, right? And in machine learning, 0 basically means there's no information. When you multiply anything with 1, it is kept as 1. It is unchanged. However, you may have something in the middle. For example, if you multiply it with 0.5, that basically says this bit of information is important. I still want this information, but it's maybe not weighed nearly as much. So basically, we have this weight, right? Weight that basically takes in our current inputs, takes in the previous input, and says, based on this information, on this conveyor belt, which bit of information should we remember and which bit of information should we forget? Does that make sense so far? Okay. Any questions? Okay, cool. All right. So again, hidden state versus cell state. Yeah. Okay, so this is kind of important here, like the distinction between this. You may notice two things. We have hidden states and we have cell states. What the cell state is that conveyor belt that I was talking about. But this hidden state is this additional piece of information that we're passing through that's a little bit different from a cell state that basically says, this is what we want to remember about the past iteration that will help us to do all these computations later, right? And the cell state is the information that we're actually keeping. So you can almost think about the cell state as the actual information we're keeping, and the hidden state as almost instructions about the previous iteration that's telling us how to deal with future inputs. And we're splitting these two because oftentimes they do actually mean different things. And again, a lot of times it's just kind of architecture design choices. So then we have something called the store gate, which is the gate that decides, given our current inputs and the hidden state from the hidden state from the previous inputs, what information are we storing onto the conveyor belts? And if you notice, before we're doing a pairwise multiplication because we're trying to forget something, we're trying to mask something. But this time, we're trying to remember something. And to remember, we use a plus symbol because we're adding information onto this conveyor belt, right? And basically what's happening is here. We first using basically the same mechanic as here, we create a mask that basically says some stuff is important and some stuff is not important. And then we use this tan H gate that basically says, okay, we take these two inputs, we process them into some sort of information that will be put on the conveyor belts. Then this mask basically says, all right, let's keep the actual important bits of the information, and then we add it onto the conveyor belts. Does that make sense? Like it's a fine distinction what's happening here versus what's happening here. What's happening here is let's decide what's going to be forgotten prior to this. So imagine this kind of conveyor belt being slowly transported here. This is saying, let's forget some stuff on the actual conveyor belts, right? And keeps moving along. And then this says, let's get rid of the unnecessary information based on the new information we have been given, right? And then this is the actual information itself, and we add these together, and it kind of keeps moving along. Does that make sense? Okay. Any questions so far? I'm seeing some confused faces.
But doesn't
Yeah.
the I sub t has the same form as the f sub t for get gate.
Right. So the reason why they do have the same form, right? If you look at the formula, it's like the exact same formula. And the reason why they have the same form is because they basically they mean the same thing in that they're trying to mask out information. Again, if it's 0, we mask that information out. We get rid of that information. If it's 1, we completely keep that information. And then obviously there's going to be numbers in between, but like we partially forget it, stuff like that. But the masks here are doing different jobs. F of t is trying to mask out unnecessary information from previous information on the conveyor belt. I of t is trying to mask out information that is being produced / given when you feed in the current inputs and the hidden state of the previous input. So that's the difference. Again, F of t is masking the conveyor belt. I of t is masking our new information. So that's the kind of distinction between the two. Does that make sense? Okay, cool. Again, like the store 10H data creates a vector of candidate values, aka the possible bits of information we're storing, and before it's being stored, we're filtering that information to get rid of the useless ones with I of t over here. Okay, again, on update gate, that's kind of what I've been talking about. The F of t is you do a pairwise multiplication, because if you look at this, pairwise multiplication basically in this case means masking. And after we do that masking, we have masked the conveyor belts, cell states, and we take this and then we bring this new bits of information, mask it, add it together. Now we've added new information onto the conveyor belts. Because, and the reason why we do this is, if you think about it, if we don't have this bit of masking here, what happens is we just keep adding new values onto this conveyor belt stuff. And suddenly the value gets so big that at some point in the future, either we have to normalize it or blows up if we have really long sequences, and suddenly we're unable to choose which information is important for certain particular time steps. For example, a certain bit of information may be important for, say, the first 10 time steps, but at the 11th time step, it may not be necessary at all because of some, say, new bit of information that's came in that determines, oh, now we don't need this bit of information anymore. For example, let's say we move from one sentence to another, right? And this one sentence to another, this new bit of information may be a period. That basically says, okay, with a period, we don't have to remember that many things from the previous sentence anymore. We can forget a lot of things from the previous sentence, but we still have to keep like 1 or 2 things for context clues and things like that. So that's kind of how you can think about this. Does that make sense? Again, all this is very abstract because it very much depends on how the machine learning scientist actually implements this. But it kind of tries to mimic the idea of long and short-term memory. Cool, awesome. Yeah, the update gate. Yeah, and again, all the trainable parameters in the LSTM are shared across all time steps, right? These parameters are the same ones we're going to be always using for every single xt that we're putting in, xt minus 1, xt plus 1. And that's kind of the power of LSTM, is that it's supposed to be this almost like moving window that's moving across the data that's able to kind of filter out information. It's very, very generalized. Yeah, again, I kind of talked about this. Now, last bit, the output gates. So what the output gate is you have this, let me see. Yeah, so basically what the output gate is you take these input, you put them through another set of weights that you're calculating, and then you take and you make a copy of the cell states, you put it through some 10H, and you do a pairwise multiplication, right? You basically do a pairwise multiplication, and you say that is our hidden state for the next output. So that's what comes in after when we put in x of t plus 1. And that's also something we output here. And we can do some things with this. Like we can calculate some sort of loss function on it. We can feed it into another neural network, depending on what your architecture is. But the point is, this kind of output gate basically says, all right, we just figured out what our memory stuff is. We just figured out what we have to store, what we have to remember. Now let's actually output something that we can do loss function so we can evaluate how well this model is doing. Does that make sense? Yeah, and it's very important here because we are making a copy of this output, right? Because that's the whole point of RNNs or RNN-based architectures, is that you have an output that you can do loss function stuff with. You can calculate what the loss is, evaluate how good the model is. But you are also passing this output along into the next time step, into the next input that you're going to be putting into this sequential data. Does that make sense? Okay. Thumbs up. Any confused? Oh, and yes.
You might have covered this already, but I just wanted to ask if you have at the very first time step, there's no like previous time step.
Yeah.
Then what would the hidden?
We just put zeros. We just put zeros, right? Yeah, we just put zeros because basically in zeros that basically means we're not affecting anything, and that's just what we do in machine learning a lot of times is filler. If you remember, like for the past few workshops we talked about padding, we also pad zeros because zero multiplied by anything is still zero. So yeah, and that's the output gate, and that's it. That's really it for LSTMs. I hope you can see why LSTMs work really well. Any questions before we move on, or technically before we take a break? Okay, cool. Let's take a break then. I guess 3 minutes, and we also have a fun little 5-question Kahoot. And afterwards, we'll be moving on to transformers, which is what everyone is actually using nowadays. All right, I'm gonna pause the recording now. Oh, this will just crash.
Oh, no, you're back. Record.
Let's-
It's not you.
Let's hope it's record.
Recording.
Okay. Oh, I think you're the one who's controlling the recording now.
Fine. No, it's fine.
Sure. You control recording.
Yeah, no, because those are so annoying sometimes.
Yeah.
Those are actually so like.
All right,
Well-
so we're doing a fun thing today, code team mode. I don't know. I think we have done this once before, but basically, you get into teams. You can get into teams of 2, 3, even do it alone if you want. But basically, all of you will be using one device and just try to answer the questions as a team.
Sweet.
We think it's pretty fun that way. Again, give us feedback if you hate team mode. But yeah, that's the link. You're free to join.
Wait, okay, you
Yeah.
join.
Again, if you're in a team, only one person needs to join.
Yeah, okay, good.
Oh, it's like.
Yeah. It's like.
Guys come over.
We also have some fun Plicos. These are really good, honestly. They're like fake ice cream. It's like ice cream cone without the cold stuff. I really like it, but that's a little prize for the first places. But honestly, I think we have to go for everyone. Cool. Person 1, person 2. I like that. Yeah, 2 people too. Okay. So the solution is every word that we want to create a vector embedding for that we'll train on. Again, the number of words and your lexicon doesn't really matter. What really matters in the case of vocabulary, in the case of actually training natural language processing models, is the actual words that we are going to be feeding into the model. If let's say, for example, like again, it doesn't have to be text data. It can be, let's say we're trying to do something with IPA or something with symbols, right? We can just have like 50 symbols and that's all we're dealing with. It's very task dependent. You may have, like for example, if you're dealing with like data that's like, if you're dealing with medical data, you may have the word pneumonia appear a lot. But if you're talking about data of like people on Twitter, pneumonia may not appear that much, especially if you're talking like political Twitter or something like that. So again, your lexicon, your dictionary entirely depends on what your input data is, and also in a way what your test data is. And that's the kind of distinction we're making here. Okay, guys, Sage in the lead. All right. Third question, it's a multi-select this time. Which of these data types will be best suited for RNNs? We get to remember what MNIST is. Okay. Yeah, the solution is audio and text, because both of these are sequential data, or in a certain way, time-based data. MNIST is a collection of handwritten digits. If you remember, we talked a little bit about it for the past few workshops. But because there is no sequential data, we don't really use RNNs on it. And in images, in this case, we're kind of referring to individual images and instead of video, So again, it's not data that has a sort of sequential quality to it or / time-based quality to it. T1 is back in the lead. We have what is the structure of an arch? Awesome. So we have inputs and the previous hidden layer going into some weights, and we have an output. That is the correct structure for an RNN. And input plus fully connected layer. Again, doesn't really make much sense because we're not passing in the layer, but yeah. So it is the previous hidden layer that's important, or the output of the previous hidden layer. All right. T1 still in the lead, but maybe Daisei will be able to catch up. Last question, what is one of the main issues with RNNs? You have a unanimous answer, and it's correct. It has a vanishing gradient problem, right? Because we're kind of passing the inputs in again and again and again, and gradients decrease every time, we have a vanishing gradient problem, even though sometimes the network itself may not be very deep because of this nature of passing it again and again, we sometimes do have a vanishing gradient problem. And yeah, so this is our podium. Again, if you're in one of these teams, come grab a thing here now if you want, later as well. But we're probably gonna have leftovers, and if we have leftovers, even those who did not make it onto the podium, feel free to grab something as well. There we go. These are genuinely really good. There you go. Come grab some if you want. All right, congrats to T1, Daisei, and XOXO. Okay.
Wait, just to make sure. So
Yes.
vocabulary means the output of the one hot vector multiplies the word embedding matrix.
Yeah.
Okay.
Cool.
Okay.
Are we continue? Okay, we have to continue recording. Okay, you want to for the sake of recording, very quickly speed run through all of this. My bad. Okay, why do we need transformers? This is the reason. Basically the idea is that we have this kind of. Originally, it was for translation tasks, and basically it uses something called encoder and decoder, where the encoder stores a bunch of information that's being fed into the decoder to generate new text. But nowadays, like people just do encoder only models or decoder only models because we don't translations are very, very specific tasks, right? So then we do something called positional embeddings, which basically tries to because we're feeding in all data at the same time suddenly. What happens is because we're feeding all data at the same time, we have to have some way of notating this position. And to notate this position, we basically use this crazy looking sign thing that basically the model's then able to learn that position 1 is different from position 0, position 2 is different from position 1. But because suddenly we're losing this kind of mathematical intuition of that, position 1 is before position 2, transformers doesn't really work that well for time series data because of this reason. All right. Now let's get back to self-attention.
Yeah, I hope everyone watching the recording understood all of that. Moving to self-attention. So yeah, again, we convert each word into a weighted average of the sequence where the important words in the sequence get higher weightage. And yeah, so basically, we want to return the values whose keys were most similar to our query. And the way we do this is first, for each of our input embeddings, we want to generate a query, a key, and a value matrix. And the way we do this is essentially, instead of learning weights in the fully connected network, we learn weights in terms of 3 matrices, such that we can do a matrix multiplication of each embedding with these matrices to determine our Q, K, and V, our query key and value. And we use the same matrix for every single input in the sequence. Now, once we have these, we want to generate a score that measures how similar they are, right? And the way we do this is, let's say this input only has 2 tokens in it, thinking and machines. And if you want to gauge how important these words are for the first word, we take thinking square matrix and make the dot product of it with every word's key. In this case, it's only 2. So we take q1.k1 and q1.k2. And again, because these are vectors, the dot product is essentially very similar to cosine similarity. Like if they were normalized, this would just be measuring cosine similarity between these vectors. So, and now that we get a score that it basically just measures how similar their keys are to our query.
Yeah. Oh, and a word on cosine similarity. That may sound very complicated, but I don't know if you guys remember how to calculate the angle between two vectors, but part of it is that it's basically almost like proportional to the dot product between these two vectors. Does everyone remember what a dot product is? Pairwise multiplication and the sum, right? Remember that to calculate the angle between two vectors, it is proportional to if you take the cosine of the dot product or something like that.
Yeah, basically A dot B is equal to magnitude of A times magnitude of B times cosine.
Yeah.
So if both magnitudes were 1, or then they would just be getting just the cosine.
Yeah. So basically, if two vectors are very similar, aka their angle between them is very small, you have cosine of 0, aka 1. So basically, you're just kind of adding them. You basically just kind of the result will be very big. However, if you take the dot product of two vectors and it's like 0 or even it's 0, that means they're exactly 90 degrees apart. Remember, two vectors, if they're exactly orthogonal, the dot product is 0. You guys will probably get to that in like Math 32A or something, even Math 33A. And if the dot product is negative, that means the angle between them is larger than 90 degrees, aka they're very far apart. So just by taking dot products, we can kind of almost measure how different two vectors are in terms of direction. And again, direction in this case is like a very high dimensional space, right? So it's much more abstract than 3-dimensional space, but this concept still stands that we have two vectors, the dot product measures how similar they are to each other.
Right. So basically, now that we have the similarity score, we basically want to just convert these into useful weights. We normalize them by dividing them by the number of elements in the vector so that they don't just cause our gradients to explode. And then we just use softmax to get them all to be proportions that add up to 1. So now we have like a bunch of numbers that add up to 1, right? And we can just use those to weight the values. So again, similarly like our search thing, the keys that are more similar to queries get higher weightage for their values.
Yeah, and again, we technically haven't covered softmax, but basically what softmax is if you're given, yeah, I know. Yeah, but what softmax is if you're given like a list of scores of like, let's say, 14, 12, 100, something like that, it basically tries to normalize that list of vectors into a list of probability distribution, right? So the higher the number, the larger the probability it would be, and the smaller number, the lower the probability it would be. It's almost like sigmoid, but like you're applying it through an entire vector. And the reason why we're applying through an entire vector is so that the sum of every single element will add up to 1. So that's what softmax is. And we actually use it for multi-class classifications.
Can softmax value can be negative?
No, it can't. That's actually one of the main reasons why we don't just divide by the total sum. Because if you want to make them add up to 1, right, you could just divide by all of their sum, by the total sum, and they will all add up to 1. But that way, if you did that, then negative values would still be negative.
But what if we got a score of negative score?
The way softmax works is it actually takes e to the power of your input and divides it by the sum of all the e's values. So because e to the power of something won't be negative, even a negative score will be converted to like a very low positive score.
Oh, so it's very low.
Yeah, and you kind of visualize what e to the power of something looks like. If you have like your axis here, e to the power of something looks kind of like this. So if you have a positive value, it kind of just kind of goes up this way. But if you have a negative value, it kind of tapers off to 0. So it kind of becomes really, really small. So to do all this e values, you kind of normalize it by all the e values, if that makes any sense.
Softmax doesn't go to negative.
It does not go to negative because
what's the graph that goes to negative? What is it? Is it tan H or a sigmoid?
That's sigmoid also doesn't go to negative. Tan H goes to negative, but again, we're not using tan H here. Yeah. So and you may be thinking of log. Log does go to like negative, which is like the opposite of e, but e is the one that goes like this, right? Like, very negative. Like it's like almost 0, and then it goes up like that. It's exponential, remember, right? So if it's negative, it's very, very small. If it's positive, it kind of just blows up to be very, very big. AKA, it's going to almost like reward really big scores, really high, so really similar vectors, basically. Does that make sense?
Yeah. So for example, if this was like minus infinity, the softmax would just be like 0.
Yeah.
And yeah.
In fact, the softmax mathematically in that case will be 0.
Yeah. Like exactly 0.
Yeah, because e to the power of negative infinity is 0.
So yeah, basically we just take all those weighted values and we sum them all up to get the output for this thing, which is basically the contextualized embedding of our x1. Now to summarize, that's basically what we're doing, except like within one operation. And yeah. Okay, so the problem with this Now, I mentioned that those actual weights we used, that the matrices that we multiplied our input by to get the query key and value were all learned by our neural network. That means they start off with random values, and then they just improve over time as our model trains. The problem with this is that we can just end up with really crappy random values, and that could just cause our model to not train well, because we end up in a situation where, let's say we have like, the dog is like sitting on the floor and wagging his tail. The word it should be correlated highly with dog, but we're going to get a situation where that just doesn't happen because the random values were just really bad. To do that, we essentially do this process we just described again and again. It is called multi-headed attention. So each one of these is called an attention head. And the logic is that if you do this again and again, you'll probably get like good values at least once or twice, right?
It's kind of like the idea, sort of like the idea of like ensemble models. We kind of talked about it where like instead of just training one model, you train like 7 different models. Like this is back in the classification and everything. You train like 7 different models and you just kind of average their outputs or like do a popular mode of their outputs and generally can increase accuracy by doing that. This is kind of in that idea where like, because again, all these key QKV, the query key and values, we're randomly initializing them. Sometimes we may get a really bad initialized value. So we basically use multi-headed attention to be able to make sure that we have some good initialization there that's able to learn. And also kind of like as an extension of that, be able to almost like pay attention to different parts of the sentence or like extract different features. But it's mostly for you know, the initialization problem.
Yeah, for regular neural networks, there's other ways to deal with this. You can just use batch norm or like Zapier initialization, but there's no analog to that for attention models. You just have to do it again and again, hope for the best. And the original paper used 8 attention heads, so that means you repeat this process 8 times. Now, what that means is that you get 8 different outputs, and you now need to aggregate them all back into a single output. Now, one would think you probably just like average them out, right? But in attention models, we're super paranoid about having our bad values affect the good ones. So instead of averaging them out, we learn another massive matrix, which is also randomly initialized. And we just matrix multiply all of that. And we just learn it such that we learn a matrix such that the dimensions are such that the matrix product is back to the size of the original one. Seems like yes.
What if that matrix is randomly initialized with bad values?
That is a good question. And our basic logic is that the more matrices we have, the better our chances are that like we just get some good ones in there and the gradients are able to just like do their work. Yeah, your main problem would be like, let's say you get a situation where all your gradients go like really close to 0, and then backpropagation isn't able to do anything because the magnitude has become so small that it's not able to learn properly. Yeah, this is just a summary of everything I just described. This is basically everything that goes on in an attention layer. But you can just think of this as like taking weighted averages. You don't need to worry about like the query key and value and stuff while you're actually working with the model. Okay, so now what is the encoder?
Yeah. Oh yeah. And before we continue, I just want to so there's this kind of article the visualized transformer, I think. Let me just bring it up real quick. Yeah, the illustrated transformer. So this is the article that we basically stole like half our figures from. This is a really, really good article if you want to really delve into a little bit more about the math of transformers. I can see we could steal a crap ton of figures from them. But if you really want to delve into the math of what in the world's going on and really understand how transformers are trained and, you know, like this is what kind of attention looks like, blah, blah,
That's
blah, blah. Yeah. My bad. This is like what the positional embedding looks like for much higher dimensions. But this really goes into a lot of detail on how transformers work. And this is a great read if you do want to know more about it and potentially even implement one yourself, the illustrated transformer. Yeah.
Right. So basically, encoder blocks are just what we just described, except it's followed by a feed-forward network. And one thing that's often omitted though in these diagrams is that almost all transformer models do these residual connections, meaning that there's a connection that takes your input from before the attention and connects it to the input after the attention. And
if you guys remember ResNets from last time, of like the whole skipping connections, it's the same thing here.
Exactly. So we basically skip both of these, and this is just so that it makes it way easier to train, because the gradients have a kind of an easier path to go down instead of having to go all the way down through the self-attention. And yeah, also one thing to be noted is that when we do this step of like weighting our values, this is sort of similar to an activation function, because as you can see, the relevant inputs get high values and the other ones kind of go to 0. But that's just the nature of it. If you think about this, when we have like 100 or 200 dimensions, chances of the dot product being a high value are really low because they probably don't point in the same direction when they have that many dimensions. So this is really causing most of our insignificant values to become really, to just go down to 0. And this is kind of why we don't have activation functions within this network.
Like we don't really have ReLUs or anything. Like in the main part of the transformer itself, you won't see ReLUs, sigmoid. You won't see tanh. You just see softmax. That's happening here.
Yeah, and in fact, you can actually even use an attention layer as an activation function, but it's like kind of experimental, and there's like one paper on it about that many citations, so I wouldn't like. It's not real super reliable, but you can do it, and it does work. Okay, yeah. So back where we were. That's now again because there aren't the self-attention there has to have dependencies because we're taking a weighted average, but the feed-forward network, all of each word passes through it in its own independent path without interacting with other words. So every word can go through the feed forward independently. And that again speeds up our training a lot. Okay, now on the decoder, this entire architecture we just discovered, we just talked about, this basically encapsulates more information about our words and uses them. But if you want to actually generate text, then we need to use a decoder. Decoders are very similar with just a couple of changes. So first of all, our self-attention is replaced by something called masked self-attention. We'll get to in a second. And our second change is that we have a second self-attention layer, which is only used if you're using the original encoder-decoder representation, where you have both encoder and the decoder working simultaneously. All we do here is we basically do self-attention again, except the queries and keys are derived from our encoder's final output, instead of generating new ones in this one. And this kind of brings our information that we use in our encoder and passes them through into our decoder. Where a decoder can use the information we just learned to make its own generations. Okay, but next, the masked self-attention. So this is straightforward. Since we're generating text, right? We don't want to look at all of our training data because if you want to generate the second word of a sentence and you can look at the entire sentence, it's not that hard of a task. We want to hide all the words that are to the right of the word we want to generate. And the way we do this is super simple. Again, when we talk about softmax, we just add negative infinity to the similarity score of every word that's on the right of the word we're generating. And what this does is that all their softmaxes go straight to 0. And we're only able to use the words that are on the left. So meaning while we're it's almost like we're simulating generating text.
You're trying to guess what the next word is, basically.
Exactly. Yeah. So again, basically each block in our decoder model does the entire self-attention mechanism we just described, goes to a fully connected layer, and then it goes through the second self-attention using the keys and values from the encoder, as you can see in that GIF. Yeah. And yep, you might have a question so each decoder adds one more word to our sequence, and after that, it takes the entire sequence it's made, throws it back into itself, and then makes the next word.
Almost like an RNN, but instead of just the previous outputs, all of the previous outputs being fed.
Exactly. And also the first one just takes in a special token to mark that's the beginning of the sequence. Yeah. Now, you might have a question about this, right? That if each decoder requires the output of the previous decoder, how is this faster than RNN? Because it's having the same problem, because it's autoregressive. It can't be parallelized. Right? Now, the key here is that an RNN needs the hidden state of the previous unit, whereas a transformer only needs the previous tokens. And we actually have the previous tokens in our training example. Meaning we can independently train it on each step. So we can have 10 decoders at the same time, training how to generate the word at positions 1 through 10. So this is kind of similar to let's say you're solving a math problem where you have 10 steps and each step also depends on the previous step. And RNN has to solve them in that order. And if it messes up once, it messes up every subsequent step as well. But with a transformer, it's like you have 10 students, you give them all the answer to the previous step and tell them to do the next step independently. So you can have them do each step all at the same time.
Yeah. So basically one of the students only works on the very first step. The second student works on the second step. And because the second student has access to the answers to the first step, they can just kind of, assume that and so on and so forth. Hence, we can still parallelize this whole process. And by the way, if you're wondering what the word autoregressive means, it just means when you have an output that's being fed into an input, it's like a chain or a cycle, Markov chain, something like to call it. Is it?
No.
Never mind.
It's not a Markov chain.
It's not a Markov chain.
Yep.
Honest estimate.
Yeah, I know. And yes, a bit what we just described, right? You take all the words on the left and you feed them to the decoder in such a way that each decoder can independently work on generating the next word without having to wait for the previous outputs. And yeah,
That basically is it for the transformer. And I want to get like a really cool example of what self-attention is really doing. So basically, as you can see back here, I think like the more important words are kind of like weighed more heavily, right? But like sometimes this can be very difficult to visualize. So I believe this is 2021. Someone basically applied this architecture to images. They used to classify images. And they actually achieved like really good performance. You can do the same with images as well. And you basically just replace a lot of the like fully connected networks with convolutional networks. And by doing so, you have something that looks like this, right? When you visualize their attention, you're actually able to see when the model's classifying images, which part of the image it is looking at to classify them, which I think is really cool. So it's kind of like visually showing you what attention is doing. It's like in like natural language processing, you will imagine kind of like attention is this, but on words. Does that make sense? Okay, cool. So right before we finish off today, I, as per the the ACM wide ethics reform, we're going to talk a little bit about kind of like the implications of all of this, of kind of natural language processing in general. So part of it is Amazon. They actually use a hiring algorithm to try to figure out which resumes are good and which resumes are bad, and basically they use that as a kind of like pre-screening process before any of the recruiters even read your resume. And basically the model was trained on resumes from like a 10-year period, most of which were submitted by men. And that basically led the model to have biases against women. Like for example, they have words are rewarded and words are penalized. And you can kind of see how, oh, by the way, Scripps College is a private liberal arts college for women in California. But like you can see like, list of rewarded words include hardworking, fraternity, engineer, director, salesman, and you have hobbies, members, Society of Women Engineers, and fired. And if you think this is just like a very isolated example, remember word embeddings? Yeah. So remember the whole word embeddings of king plus minus men plus woman equals to queen, right? What if we put that to just random everyday words? So let's apply this idea to just a bunch of words. For example, uncle to aunt, right? Uncle minus man plus woman equals to aunt. Makes sense? Lion to lioness. Surgeon to nurse. Architect to interior designer, beer to cocktail, professor to assistant professor. And if you put an assistant professor here, it'll give you, sorry, professor, associate professor. If you put an associate professor here, it gives you assistant professor. So you can kind of see how by giving like data sets that are inherently biased, we can have ML models that have this bias in there that basically, like inherently has this idea of like, this imbalance between what these vectors mean. And that entirely again depends on your word input. If the text you're giving it is inherently in some way sexist, it's going to learn the sort of inherent like sexism that's in there because that is what's going to help it to predict words, right? And by the way, credits to Kai Wei Chung, which is CS M146, the introduction to machine learning class. This professor, he does NLP research, and this is the example he shows of the importance of AI fairness. And I think it's kind of funny, but also kind of sad at the same time. And that is why with machine learning, a big part of fairness starts from the data, because a lot of times we can't really control what the model's learning. Again, it's just gradient descent. We're just feeding in, hoping, and again, we're evaluating it on metrics that are also based on data, right? So like the evaluation itself almost is also rewarding the sort of behavior. So starting with fair data and starting with good data is very, very important. And yeah, that is, any questions before we go for today? Cool. There's some other resources. And yeah, thanks for, I think that's the last slide. That is the last slide. Okay, thanks for coming for today. What we're going to be talking about next time is, I believe we're going to be talking about something called back propagation, which is, first of all, how in the world do we actually calculate gradients? We keep talking about gradients. How do we have a neural network and how do we calculate gradients? And we'll also give a little demo, a little introduction into Python and specifically PyTorch and how we can build neural networks with PyTorch. Thanks for coming for today and hope to see you next week. And good luck on your midterms if some of you still have ones that are left. Take a snack if you want to.